Okay. All right, students. Welcome to the second week of this course. This is week 2 of CS 3303. This is the instructor clause. I am just going to spend the next few minutes. We just wanted to talk about week 2. During this week, we're going to be covering, let's pull it up here. We're going to be covering the sections 2.4 to 2.7 of the textbook, and we're going to be covering subjects such as integer and floating point representation, character codes, error correction, and detection. What I'll do is, even though for the first week we covered chapters 1 all the way to 2.3, I think I'll just start this week with sections 2.1 of chapter 2, just to kind of quickly recap those sections, and then we'll go from there. This video may be a little bit longer because I want to explain some concepts which I think some of you may struggle in the class. I want to explain some of those concepts, and also introduce some videos that would be helpful for you guys to understand some of the subject matter that we'll be covering in the course. Okay, so we're going to be covering the sections. All right. So what I want to do is today I will try to use the slide deck that was prepared for this course as opposed to the textbook as I did last time. So we'll go to the slide deck for chapter 2, and we'll just go to the slide deck, and I'll try to explain some key concepts within this chapter. I have this document which I have prepared for you. I will be collecting some notes as we go, and at the end of the session I'm going to give you some videos that I think will be helpful to explain some of those concepts which I think will be a little bit needing a little more explanation. Okay? All right. So in this section we're going to be talking about data representation, how data is represented in computer systems. All right, computer systems really deal with binaries, zeros and ones. At the end of the day, it's really about binary, 0 and 1s, and we're going to be talking about how that data is represented. So we're going to be trying to understand the fundamentals of numerical data representation, and there's going to be a lot of conversion, right, between different bases, converting between a base 10 to base 2, and we call those different radix systems. And then towards the end, we're going to talk about some error checking, CRC error checking, and just some fundamentals around that. And there's going to be a lot of courses. There's lots of videos online that you all can look through to understand some of those details about CRC checks. So we're going to be understanding the fundamental concepts of floating point representation. I think this is a very interesting subject. We're going to talk about some character codes and error checking codes. Okay, so we talked about this briefly in last week. A bit is the most basic unit of information in a computer. It all starts with a bit. It's either on or off. If you look at digital circuitry, if you all remember the Matrix and how the movie starts and you see all the stream of bits, that's really the internal representation of a computer. It's all about zeros and ones. Okay, and in the byte, we talked about the byte being 8 bits, and a byte is the smallest possible addressable unit of a computer system. Okay, a byte is 8 bits, and is the smallest possible unit, addressable unit. Okay, so you probably heard of 16-bit machines, 32-bit machines, 64-bit machines. A lot of machines today are 64-bit machines. I think my Mac is a 64-bit machine. It means that when the computer tries to grab instructions from memory, it's grabbing instructions as 64 bits of information. 16-bit computer will be grabbing 16 bits of information, 32 bits. 32-bit computer will be grabbing 32 bits of information at any given point in time. Okay, so in a word addressable system, a word is the smallest addressable unit of storage. So in a 64-bit system, 64 bits is the smallest addressable unit of storage in the machine. We talked about 4 bits being a nibble. We talked about all of that last class, so no need to talk about that more. And, we talked about bytes, store numbers using the position of each bit to represent the power of 2. I think in the textbook, there's some exercises on how you take a decimal and you convert that into binary representation, right? So, like, for example, I think on page 62, example 2.1, it shows you how to take the number 243 and convert that to in the power of 10. And you can do something equivalent in the power of 2. Now, we use base 10. So when we talk about 1, 2, 3, 4, 5, we're talking about in base 10. So I think in this same chapter, there's examples on how to convert from one base to another. Okay, and an integer number can be represented using any base or any radix, right? A number 10 can be represented in base 1, in base 2, in base 3, in base 4. Any number can be represented in any base or radix. Okay, so this is a very good example. If you take the number 947, for example, right? 947 is 9 times 10 to the 2. 10 to the 2 is 100. Okay, so 9 times 10 to the 2. The 2 represents these two positions. Plus 4 times 10 to the 1. And plus 7 times 10 to the 0. Something equivalent for this one. This is 5 times 10 to the 3 because this is the thousands. Plus 8 times 10 to the 2 because this is the hundreds. Plus 3 times 10 to the 1 because this is the tenth. And then now here's where you get interesting though. When to represent the decimals, you have to now represent to the exponent of negative, right? So it's going to be plus 4 times 10 to the negative 1. Negative 1. So the number of positions after the decimal point is the exponent. Okay, so plus 4 times 10 to the negative 1. So I think we talked about this last class. So let's not dwell on that too much. So these are positioning numbering systems. Okay, so let's keep going. Let's see, where are we here? Okay. Another example, right? So this number is represented in binary. Again, binary is base 2, right? Base 2. So you take a number, you convert it to base 2. And to convert this, to get the decimal equivalent of this is 1 times 2. Remember, the base is 2, the radix is 2. So 1 times 2 to the 4, right? If you look at this, 4, 1, 2, 3, 4. 1 times 2 to the 4 plus 1 times 2 to the 3. And if you do that, this number is 25. Okay. And we say when the radix of a number is something other than 10, the base is denoted by a subscript. In our first assignment, there was some confusion because the numbers on the left did not have a radix. And my instructions was that if a number does not have the base explicitly indicated, that means that number is represented in base 10, right? If a number does not have the base explicitly stated, that number is represented in base 10, right? So you don't have to write 25 base 10 like this. We just generally write 25, and 25 is, so we don't do 25 base 10 when we're writing stuff, right? Where's the superscript here? We just do 25. I am not very familiar with this Google Docs, but anyway, I think you guys get the point I'm trying to make here. Okay. Moving on. Let's see where we are. All right. So converting between bases. You can convert from one base to another. If we go to the next slides, let's see, there are two methods. So yes, in the previous lesson, I remember trying to convert a number from one base to another. There's two ways you can usually do that. There's the divisional method and there is the subtraction method. Now, let's see what the slide is saying. Suppose you want to convert the decimal number 19 to base 3. We know that 3 to the 5 is 243. So our result will be less than 6. Now, I am not a big fan of such. I am generally the fan of doing the models. Let me just go down the slide and see if this is the other one that I'm used to. Let's say 190 minus 162 equal to 3 to the 4 times 2. But the question is, how did you find out? How do you know about 162? So this is one format. Now let's keep going down. Let me see if so this is one format. So you folks can read through this one, but I'll be honest, I am not very familiar with this one. What I'm familiar with is the divisional method. Okay? This method is mechanical and easy. It employs the idea that successive division by a base is equivalent to successive subtraction by powers of the base. All right, so let's use an example. So 193, you want to convert this to base 3. So what you do is that you divide 193 by 3. This is the divisor. You divide this by 3. How many times does 3 go into 193? Is 63 times its remainder. And you keep dividing. So you say, okay, how many times does 3 go into 63? 21 times its remainder. You keep dividing until, again, how many times does 3 go into 21? 7. There's a remainder. You capture the remainder. And you keep doing that until you can divide no more. And then the answer becomes 21001. So this is the method I am familiar with. And I think we talked about this last class. Okay, so if there's any questions on this, feel free to reach out to me, but there's lots of YouTube videos that your folks can watch on this one. So this is the divisional method. Okay. Fractional values can be approximated in all base systems as well. So not only in base 10, you can have fractions represented in all bases as well. And this says, unlike integer values, fractions do not necessarily have exact representations under all radiuses. All right, the quantity half is exactly representable in the binary and decimal systems, but it's not in the ternary base 3 number system. Now, let's see how to convert a fraction. So 0.47 base 10. Remember, when we write things in base 10, we do not explicitly talk about the base, but 0.43 base 10 is, we talked about the fact that because this is a decimal, the base, the exponent, the exponential factor is going to be negative, right? So it's going to be 4 times 10 to the negative 1 because the 4, all the numbers are after the decimal point. So 4 times 10 to the negative 1 plus 7 times 10 to the negative 2. Okay, now this is 0.47 in base 10. Now let's do, how do you represent 0.11 base 2 to base 10? How would you convert this to base 10? This would be 1, this one, times the base 2 to the power minus 1, plus 1, this other 1, times the base 2 to the minus 2 again. The exponent, the power, is the number of places to the right of the decimal, but negative sign. Okay, this is half plus 1/4, which is 0.75. So this in base 2 is 0.75 in base 10. Okay, so there's examples in the textbook that you guys can go through. I think those are, there's some examples here, page 66. Page 66 gives you some of those examples. All right. So let's see what else we want to talk about. All right, so let's keep going. Got a lot to cover here. Let's keep going. We can skip this slide, just talking about converting between bases. There's the subtraction and the division method. Again, I said I prefer the divisional method because it's a little bit mechanical and easier to understand, but you all can read through that. Now, this one is what are we doing here? So the calculation to the right is an example of using the subtraction method to convert. So you folks can go through this example. Like I said, I'm not very familiar with this example, I'll be honest. I didn't learn it this way. So, but you folks can go through it and see if you can make sense of it. But again, either way works. At the end of the day, if you have one method that you understand fully and that method works for you, pick that method. Okay. Now using that, so this is another way. You use the multiplication method to convert the number 0.8125 to binary. We'll multiply this by 2. Let's see, what does this do? Okay. We multiply that by 2, we get this. Then we take this part, after the decimal, multiply it by 2, we get this. And then we take this part and multiply it by 2. And I see, if you notice, we keep dropping the portion of the number that is before the decimal point. Again, some methods I'm not very familiar with. I learned these things a long time ago. And the method I'm more familiar with a little bit different. But as you see here, when you multiply 0.8125 times 2, you get this. We're discarding the 1 here. You are finished when the product is 0 or until you have reached the desired number of binary places. Okay, so in this case, the product is 0. 0.8125, you multiply that by 2, you get this, you discard the 1. 0.625, you multiply that by 2, you get this, right? And then you discard the 1 again. 0.2500, you multiply that by 2, you get this, you discard this part. And then 0.5, you multiply that by 2, and then the answer becomes this. 0.1, no, you start from up here, 1102. So you're really converting 0.8125 in base 10 to base 2 using the multiplication method. So lots of examples on YouTube that can demonstrate this. Okay, so let's see what I want to talk about. Hexadecimal is another interesting numeric system. I think we talked about it briefly last class. We can quickly skip through this because what I want to cover, these ones, there's pretty straightforward. We wanted to start talking about sign representation. The most important thing to understand with signed representation of numbers is that the high order bit, which is the leftmost bit, is also called the most significant bit, is used to indicate the sign of the number. Okay, so if you have 8 bits, if your computer is storing information 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, this bit is the high order bit, is the most significant bit. Okay, you typically hear this being called the most significant bit because this one has the most value, right? Remember, this is 1 times 2 to the power of 1, 2, 3, 4, 5, 6, 7. Okay, so it's the most significant bit. This bit for signed numbers, this bit is reserved for the sign. So if this bit is 0, it typically indicates that we have, is it a positive number? I gotta check. And if this bit is a 1, it indicates a different sign. Okay, so for signed numbers, the most significant bit is used for the sign, while the remaining 7 bits in an 8-bit system is used to represent the data. Okay, so that's what we're saying here. 0, yes, is used to indicate a positive number, and 1 is used to indicate a negative number. And then the remaining bits are used for the value. Okay. And now it says there are 3 ways in which signed binary integers can be expressed. Assigned magnitude, 1's complement, 2's complement. We're going to be talking about that real quickly here. And in an 8-bit word, signed magnitude representation places the absolute value of the number in the 7 bits to the right of the sign. So if we go back to here, okay, this bit will be the sign, In this case, is a negative number. And this would be the absolute value of the number. So I have a little calculator here. So let's say that I wanted to convert this from base 2, and I wanted to convert it to base 10. Convert, so that's 127. So this number here, not here, this number here should be, because this is a 1, which indicates a negative, this number should be minus 127 base 10. Okay, minus 127 base 10. Now let me see here. It says, yeah, I don't know if we can put signs here, but yeah. Okay, so that is this. That is how you represent sign numbers in computers. The most significant bit is used to represent the sign. And that's what's referred to as an 8-bit signed magnitude. Now let's talk about 1's complement. Let's see what this is. I think this is another example. Yeah, so this is an example of an 8-bit signed magnitude. So plus 3, remember plus 3, the most significant bit is a 0, which represents a positive number. And we are using 8 bits to represent the information. So all these bits will be 0. And then these last 2 is what actually equates to 3. And then negative 3, the most significant bit, is a 1 that represents negative. And then again, the magnitude is a 3, right? All those bits are 0. And then the least significant 2 bits equate to 3. Okay. So let's keep going. You can just, again, the slides are pretty straightforward. Stuff is pretty straightforward. Let's see where we are here. We are on, where are we? Where are we? Let's see. We did that already. Okay, let's see. We went through this. Good. So we're in slide number 30. All right. So binary addition, easy stuff, right? When you want to do binary addition, you just take the binaries. There's some basic rules in binary addition. 0 plus 0 equal to 0. 1 plus 0 equal to 1. 0 plus 1 equal to 1. Obviously, 0 plus 1 is the same as 1 plus 0. And this is where it gets interesting. 1 plus 1 is equal to 2 decimal, but if you convert 2 decimal to binary, it's equal to 1 0. Okay? So if you think about it, 1 plus 1 is equal to base 2, 0, and you carry a 1. In fact, let's do that real quick. So if I do 1 plus 1, okay, is equal to, because we're doing in binary, the highest number in the binary is 1. So once you do 1 plus 1, that is 2, and there's no 2 representation in binary, so that becomes a 0, 0, and then you carry the 1. Okay? Another way to think about it is that 1 plus 1 is 2 decimal, and if you convert 2 decimal to binary, it's 1 0. Think about it this way. If you did, let's say, let's use base 10, because you all are familiar with base 10. Let's say we did 9 plus, we're doing base 10, 9 plus 9, which is 9 plus 9. Oh no, let's say, yes, 9 plus 9. 9 plus 9 is 18, so we have 8, and we carry 1, and this is base 10, right? So, yeah, this is base 10, right? So it's kind of similar. 1 plus 1 is 2, but there's no 2. There's no 2 in binary, in base 2, so we have a 0, and then we carry 1. I don't know if I'm explaining this correctly or not, or clearly, but That's the idea here. Okay, so that's what this is. That's why this is what it is. And then, of course, it makes this simple for digital circuits to carry out arithmetic operations. That's what it is. So let's go down. This is again sign representation. Nothing much to talk about here. If you wanted to add binary notation, you just converted two numbers to binary and you just add them, 1 plus 1 plus 0, and just follow the rules in the previous page to walk you through this. Pretty straightforward stuff. If you have any questions, please reach out to me. So let's skip the slides real quick. So we're going to run into a subject around carrying. We talked about the carry in the previous example where we did 1 plus 1 is equal to 0, and we carried over the 1. So that's carrying over. Okay, so we're going to be talking about that. Let's see here. Let's see. I want to see if we have a very good example. So I think in this one, we're going through an example here. So if we do 1 plus 0 is 1. 1 plus 1, remember I talked about the fact that 1 plus 1 is 0. And you carry the 1 and you put it up here. Okay? Now, when you add 1 plus 0 is 0, is 1 plus 1. Again, this will be 1 plus 1. 1 plus 1 again is 0. You carry the 1. And you keep carrying and carrying and carrying and carrying and carrying until you get to the last most significant bit. And then you may have to carry over that 1. That becomes a carry. That becomes a carry. And that carry bit is very significant because if the amount of bits that the computer has available to store the result is not wide enough. Let's say that we're doing what? There's 1, 2, 3, 4, 5, 6, 7 bits of information here. 1, 2, 3, 4, 5, 6, 7. So let's say that we're storing 7 bits of information. Okay? Obviously, this is signed data. If the mathematics here resulted to a carry over, and we were carrying over into the signed bit, that becomes what they call an overflow. We're going to be talking about that, and that becomes a problematic situation in computer systems. Overflow. So we can quickly skip through this. This is very simple examples. Again here, let's see. So yeah, so these two values whose sum would fit into the 7 bits. And as we're saying, if that's not the case, we have a problem. If the sum does not fit within the 7 bits, we have a problem. Now let's see what the next slide says. All right, so this is a good example. In this case, let's see. We see that the carry, which is this one, which has been carried over, these ones were being carried over. The carry from the 7th bit overflows and is discarded, giving us an error. Because remember, if this was an 8-bit system and we're talking about signed numbers, that most significant bit is used to store the sign, right? But given that there's an overflow, we have to discard it. But this was useful information. This is important information. And because we discarded it, the result is not represented correctly. And this is what we call overflow in arithmetic, in mathematics. Very important concept, overflows. Very important concept. Okay. So that's what this is. That's what this is. So signs, you also add the signs. You know, if you're doing signed math, these are the signs. You also add the signs. 1 plus 1 equal to 1. Now, they say because the signs are the same, all we do is add the numbers and supply the negative signs. Oh, sorry, you don't add the signs. In the case where the signs are the same, you just use the same sign. In the case where the signs are different, in this case, let's see, mixed sign is done the same way. Let's see, so what was happening here. We are adding, and at the end of the day, the sign is negative. So the sign of the result gets the sign of the number that is larger. Okay, so the sign of the result, in this case, gets the sign of the number that's larger. This number is larger. And the sign of result, when you keep adding this, gets the sign of this number that's larger. That's what's happening here. So please feel free to read through this if you have any questions. reach out. Okay, so I just want to skip through this real quick so we can talk about some important concepts I wanted to cover real quick. You guys can read through this. Some concepts called the diminished redox complements of a non-zero number n in base. So some formula that you can use to just formalize some of the stuff that we talked about in the previous slides. Now, there is something called 2's complement and 1's complement. So I have some notes here. If I can find my notes here, let's see here. 2's complement and 1's complement. If I can find my notes, 1's complement is 2's complement. Let me see if I can find my notes. If not, we'll keep going down the slide deck and I should be able to find that section here. Yes, so the 1's complement. So in page 74 of your textbook, it talks about the 1's complement. Right, it talks about the 1's complement, and this is where this formula comes in. So if you have a number n in base r with d digits, it's represented by this formula. It's represented by this formula, and in your textbook on page 74, it gives you some examples. Okay, so this is what is known as, what is the textbook say? I think this is what is known as the let's see, the 1's complement. Yes. Because in that section of 1's complement, a few experiments will convince you that forming the 1's complement of a binary number amounts to nothing more than switching all of the 1's with zeros and vice versa. In other words, you take a number, you take a decimal number. Let's do that. In fact, let's do that. So you take a decimal number. Let's say that you take the number 4. Decimal 4 is equal to, represented in 4 bits binary, is going to be 0, 1, 0, 0. Okay, so that's 0, 1, 0, 0. This is 4. And to represent 4 in, so this is 4 represented in binary or 2's complement. Now to represent this in 1 complement, you just convert the zeros to 1 and the 1's to 0, and you add a 1. So that becomes 1. Now we'll start from here. We'll start from this significant bit. That becomes 1. Excuse me, that becomes 1. That becomes 0. That becomes 1. Okay, we just flipped the bits around. Right, 1, 0, 1, 1. And then if you add a 1 here at the end, you add a 1. Add a 1. And then if you add this up, remember 1 plus 1 is equal to 0, and you carry a 1. You carry the 1 up top here, that becomes 1 plus 1. Plus 1 that you carried becomes 0. And you carry the 1 again, and then that 1 plus this 0 becomes 1. And then you have 1. So this becomes the 1's complement of 4. You take the 2's complement, you flip the bits, and you add a 1. Okay, so page 74 of your textbook talks about that. Read through that, and if you have any questions, just please feel free to send me an email. I think, let's see if this is what we're talking about here. So yes, so if we look at this one, using 8-bit 1's complement representation, plus 3 is, this is the 2's complement though. This is the binary representation of 3. And yes, okay, so if you look here, the 1's complement is, you take this bits, you flip 1 to 0, 1 to 0, and then the zeros to ones. And then I thought you added a 1 in the ones complement as with any sign magnitude. Negative values are indicated by a 1 in the higher order bit. Okay, so we need to have to make some clarification here. Page 74 of the textbook talks about the fact that the ones complement is the same as switching all of the ones with zeros and vice versa. Oh yes. So I take that back. You flip all the ones to a 0 and vice versa. You flip all the ones to a 0 and vice versa. So that's the ones complement. So back to this example, we flip the ones to a 0 and that's it. So the adding of the 1 is not in this particular case. There's a case where we flip and we add the 1, and I think, let me see here. Yes, that would be in page 74 of the textbook. Okay, so we'll get to this. But just ignore that for now. Ones complement, you take the binary representation of the number and you flip the bits, zeros to 1 and ones to zeros, and that becomes the ones complement. Okay, so let's just stick with that for now until we learn more. Okay, so let's see what happens here. So with ones complement addition, the carry bit is carried around and added to the sum. All right, so let's see what happens here. So these are two numbers binary represented. You add the numbers, 0 plus 0 is 0, and you keep adding. 0 plus 1 is 1, 0 plus 1 is 1, you keep adding. At some point, you have a carryover. Like in this case, 1 plus 0 is 1. 1 plus 1 is 0, you carry a 1. 1 plus 1 is 0, you carry a 1. 1 plus 1 is 0, you carry the 1, and then you add the 1. That's what I was talking about in the previous one. You add the 1, and that becomes this, and then that becomes the result. So yes, you add the 1, but I didn't really kind of remembered the reason behind that, but it's because that 1 typically is an overflow. Okay, so we note that 19 in binary is this. So negative 19 in ones complement is this. You see, you just flip those bits. 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0. So sorry, 1, 1, 1, 0, 1, 1, 0, 0. Okay, that's what this is right here. So I'll let you folks read this carry. Remember, carrying over is when there's an overflow. No, carrying over is when there's a bit. When you add two numbers and the result exceeds the highest number in the base range, you carry over, and you keep carrying over. And an overflow is if the amount of memory that the computer's reserved for that number is not enough to contain the result. You have an overflow, and that overflow typically results to an error in your computer program. Okay, so I'll let you go through the slides, and this is all straightforward stuff. If you have any questions, please let me know. So now I want us to talk about the Booth algorithm. The Booth algorithm is a mechanism that allows us to be able to do binary multiplication. Okay, so let me see here. Here's the Booth algorithm in a nutshell. Okay, there's some rules around Booth algorithm. It says if the current multiplier bit, now the multiplier, this is the multiplier right here. Okay, this is the multiplier and this is the multiplicand. So if the current multiplier bit is 1 and the preceding bit was 0, subtract the multiplicand from the product. if the current multiplier bit is 1 and the preceding bit was 0, you subtract the multiplicand from the product. And if the current multiplier bit is 0 and the preceding bit was 1, we add the multiplicand to the product. If we have 0, 0 or 1, 1 pair, we simply shift. So these are some rules, right? So if the current multiplier bit is 1 and the preceding was 0, we subtract. But in the case where you have a double 0 or a double 1, we simply shift. In this case, we had a double 0 and a double 1, we shift. Okay? And then in the previous case where the current multiplier bit is 1 and the preceding bit was 0, we subtract the multiplicand. In this case, we're subtracting this from the product, right? And then in this other case where the product, we subtract it from the product, and then when we have a double zeros, a pair of zeros or a pair of 1, we shift, and then in this case we add. Now this booth algorithm, there's a video which I have prepared, which this is a YouTube video which I was able to source. This is an excellent video that describes the booth algorithm. I recommend you folks go to this video. This gentleman does a way better job of describing this algorithm than I can do in the next few minutes. But please go to this video, take a look at it, understand it thoroughly, because I can guarantee you that some concepts of the booth algorithm would feature in your quiz or in some of the exams, okay? It's an interesting algorithm, take a look at it, but it's really just, there's some rules of the game based on the multiplier, based on the multiplier and the multiplicand, right? The sequence of zeros and ones, and if the zero, based on that pattern of zeros and ones, there's some rules of the game which determine if you should be shifting, because when you shift left or you shift right, you're either multiplying or you're dividing the number. If you should be shifting, adding, or subtracting. So please take a look at this video. I'll put it in the announcements for the week, and I'll also update the course. And please spend some time to understand the booth algorithm. Okay, so that's booth. In a nutshell, real quick. More examples on the booth algorithm. This slide talks about overflow, which again, please go through this. I talked about that. Carry and overflow. Typically, when you have an overflow, there is generally a problem. As you can see here, when you have an overflow, in those two cases where you have an overflow, there's a problem. Okay, so go through that. And if you have any questions, please let me know. Now we talked about shifting. In the booth algorithm, in some cases you shift left. When you shift left, you're typically multiplying by 2, right? A left arithmetic shift inserts a 0 in for the rightmost bit and shifts everything else left 1 bit, and in fact multiplies by 2. Let's do a quick simple example here. So, and this is important for you to understand the booth algorithm. Okay, and please go to that video again. Now, if I take a simple number like 4 in decimal, which is 0100. Okay. If I wanted to shift left, just one space, 1 bit, this binary representation of 4, okay? What you do is that you put in a 0 at the end. So it's going to be 0, 1, 0, 0, 0, because we've shifted. We've moved this whole thing towards the left. Oh, sorry. We've moved this whole thing towards the left, right? And when you move all the numbers towards the left, you've created one space, 1 bit, 1 empty bit, and you just put in a 0 there. If you were to convert this, to convert this to decimal, this is 2, so 1 times 2 to the power of 1, 2, 3, 4. So this is 1 times times 2 to the power, I'll just represent this how you do in computer language. 2 to the power, where's to the power is, yes, to the power of 4. Why 4? Because this is in the 1, 2, 3, 4. Okay, and this is 16. This is 8. 1 times 2 to the power of 3. No, so 4 is, this is 4. 2, this is 1 times 2 to the power of 2. And this is 1 times 2 to the power of 3. So this is 8. This is 8. So shifting left is equivalent to dividing by 2. Shifting left, sorry, is equivalent to multiplying by 2. So if we do this, put it here to decimal, that is 8. Okay, so let's shift this thing left again. Remember, shifting left is just adding 1 0 at the end of the number, and this would become 16. You see that? Let's shift the left again. This would become 32. Shift it left, it becomes 64, right? So for each left shift, you're multiplying a number by 2. That's what that's all about. Okay, so that's what this is. And shifting right is dividing by 2. So if you imagine, if shifting left means that you're adding a 0 at the end, shifting right means that you are actually adding a 0 in the front or taking a 0 away from the end. All right, so this becomes 32. Let's shift right again, taking a 0 from the end because again a 0 is going to be in the front. This becomes 16. Let's shift right again, add 1 0 here, take 1 0 off. Remember, it's fixed number of bits. So shifting right, you're dividing a number by 2. Okay. So that's shifting. We'll just quickly speed through this real quick. Floating point, again, I just wanted to kind of quickly talk about floating point, how floating points were represented in computer systems. Let me see if there's a graphic here. Yes, so you can read through the sections, but I just wanted to just, you can read through the sections, floating point 0.5. Let's see what we're talking about here. Yes, we talked about this, how 0.125 is 1.25 times 10 to the negative 1. And you can still also represent this as 0.125 times 10 to the negative 2. No, 0.125 times 10 times 1 times 10 to the 0. You can still represent that. Now, the way floating point numbers are represented in computer systems, 3 parts. There is the sign. There's the 1 bit that's reserved for the sign. There's a number of bits that is reserved for what is called the mantissa. And there's also a number of bits for what is reserved for the exponent. So if you remember, 0.125 it's a positive number, so obviously it's plus 1.25 times 10 to the negative 1. The mantissa is the part that represents the number, that represents the number, and then the exponent captures the decimal places. Okay, so it's 10 to the negative 1 because this was a decimal 0.125. And this information is covered in sections 2.5. Booth is covered in section 2.4, and this information is covered in section 2.5. Okay, so read it. There's a simple model in there. It talks about the mantissa and the exponent. And it keeps going on. There's so many examples in there. We talked about normalization. Normalization is the rule that says that the exponent should always start with, the exponent should be represented. Let me see here. Because synonymous forms, I'm reading page 92, by the way, are not well suited for digital computers, floating point numbers must be normalized. Okay? And that is the leftmost bit of the significand. The leftmost bit of the significand. Now, the significand is the mantissa. The mantissa and the significand are the same thing, because on page 90, it talks about the mantissa is widely accepted, but the IEEE, which we learned last class, they introduced the term the significand to refer to the fractional part of a floating point number, combined with the implied binary point. So the significand is this. The significand is the exponent. Oh, these books are confusing here. The exponent. Oh, yes. Okay, yes. So the significand is the part that holds the mantissa. Okay? So before we get there, so the number 0.125 is represented as 1.25 times 10 to the negative 1. So this is the mantissa, and this is the exponent. Okay? So 0.125 is 1.25 times 10 to the negative 1. Again, the mantissa is 1.25. The exponent is 10 to the negative 1. Now, how does a computer store this? Okay. So the way a computer stores this is that the sign is stored in the most significant bit. The exponent, that's why I was just getting confused here, which is 10 to the negative 1 in the prior example, is captured here. And then the significand, which is this part, captures this one, the mantissa. Okay, so that's what this is all about. Okay, so this captures the sign, this captures the exponent 10 to the negative 1, and this captures the significand. Okay, so let's see, that's another example. In the textbook, we talked about the floating point number is 14 bits in length. 14 bits in length because the sign bit is 1 bit. We reserve 5 bits for the exponent, and then we reserve 8 bits for the significand. And then it keeps talking about some more stuff here about this. So this is an example where this is a positive number because it's a 0. This is the exponent. We put 110, which is 6 in base 10. So this is the exponent represented here. And this is the significance. So I think this number, let's see, we know that 32 is 2 to the power of 5. Yes, 32 is 2 to the power of 5. So in binary, 32 is 1.0 times 2 to the power of 5. Everybody agree? So because 32 is 2 to the power of 5, which could be represented as 1 times 2 to the power of 5, which is also equal to 0.1 times 2 to the power of 6. This is normalization. This is normalization, right? 0.1 times. So if you read, let's see, I think this is page 92 of your textbook. It talks about normalization. And one of the videos I have here also talks about normalization. But so to represent this in the way the computer will store this is we have 0.1 times 2 to the power of 6. Okay? So this 2 to the power of 6, this exponential factor of 6 is what is stored here. And then 0.1 is all of this here. Okay? So there's a prior part where we talked about how you convert decimals to binary. This is 0.1. So that's why you see it's positive. This is the exponent, and this is the significand. Okay. So different representations of the same thing. This is 6. This is 0.1 times 2 to the power of 6. This would probably be, let's see, this is 2 to the power of, what is this? This is 6. This is 7, this is 8, so this is probably 0.01 times 2 to the power of 7. But several different representations of 32, and that's why you have normalization. Normalization says that let's not use 4 different ways to represent 32. Let's pick one and abide by that one. Okay, let's pick one and abide by that one. So that's normalization. Okay, so read through this. Now it says to resolve the problem of synonymous forms where you have different ways of representing a number, we establish a rule that the first digit of the significand must be 1. So if you go back previous slides, the first digit of the significand, which is this pink box, should be 1. So this is the normalized form. This is the normalized form. Okay. So that's normalization. Let me see. Yes. So this process called normalization results in a unique pattern for each floating point number. And in our simple model, all significance must have the form 0.1 da 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 da. Okay, so 32, if you go back to our previous example, that's why we said 32 is the normal form of 32 is 0.1 times 2 to the power of 6. That's the normal form. So if you take this one, 45 can be represented as this in binary, which can be represented as this again. Remember, this is 100.1 times 2 to the power of 0, which can also be represented as 1.001 times 2 to the power of 2. Now, this is the normal form because, again, remember, the normal form says that all significance must be of the form this. This is the normal form. Okay, so it's very important. So read through that. If you have any questions, please let me know. And this just talks about negative numbers. I think we continue to talk about the floating point representation. But again, this should be relatively straightforward. Once you understand, the significand and exponent and, converting fractions to binaries, this should be relatively straightforward. We talked about the IEEE. IEEE is just extending that simple model. So instead of 5 bits as the exponent, IEEE's model says there's an 8-bit exponent and a 23-bit significand with the bias of 127. Now, this concept of bias is something that I have prepared a video, but the bias just gives you a range of possible numbers and where your 0 will be. So a bias just says that your exponent may go from negative 128 to 128. Okay, with 0 as the middle point. But I have prepared a video, a YouTube video, one of these links here that talks about which one is this? I think it's floating point numbers or excess notation. So read through that and you'd understand the concept of bias. Okay, concept of bias, because you just want to be able to have a range that the exponent is expressed through. Okay, so this is an example of negative 3.75 using the IEEE single precision. You first of all convert it to binary, which is this, and then we talked about normalization. Now there's the bias of 127. So the way the bias system works is that you add 127 plus 1 equals to 128, and this becomes our exponent. Remember, you always want to fit the number between that bias range. If the bias is 127, it has to fit between negative 127 and negative 128 and positive 127. Oh no, negative 127 and positive 128. And then so you add 127, you add 1 to the bias, that becomes 128, and that becomes our exponent. And where did this one come from? This one came from the exponent, right? The power of the exponent. You add it, that becomes 128, you represent that, that is what we store in here. And then here, the first one in the significance is implied. So we have this. Okay, so that's what the whole bias is all about. So read through that. That's covered in in sections in pages 95, 96, covers all that stuff. And again, I've prepared a video for you on that. Okay, so if you have any questions, please let me know. Let's see what else we've got here. So I wanted to cover this because I think this is a tricky concept. Again, the concept of bias really is just how you have a range that you want to represent the exponent through, so that you can fit that within this bits. You can fit that within the spaces allocated by the computer, and then the significand is normalized. So those are the most key important concepts that I wanted to talk through. So triple E, again, just another way of representing floating point numbers. Read through that. There should be nothing challenging there. And how to add floating point numbers. Really, you're just doing, again, binary arithmetic. Where if you just look at these two, you're just doing the binary math here. And you always have to watch out for those overflows, though, right? Because if you have overflows, the result may not be correct. Okay, so just take a look at this and make sure you understand it. And if not, please feel free to check out YouTube videos, or you can always reach out to me. And multiplication, very similar. Again, if you think about how the Booth algorithm works, or you just multiply these two things, you should be able to get those answers. Okay, so just more stuff about floating point representation. We talked about overflow, where the amount of memory used to store the information is not big enough, so some bits overflow out of that register, and then you lose data. Underflow is when the divisor, the thing that, so you have the number that you're trying to divide, the number that you're dividing by, I think it's called a divisor. It is called a divisor, right? So if that number is too low, it's almost like dividing by 0. You can have an underflow. Okay, and it typically result to a crash in your computer program. Okay. So there's a section that talks about range, precision, and accuracy. I think you all folks should be able to understand this. Nothing for me to talk about here. Read it, and if you have any questions, let me know. Range really is dependent on the number of bits that is used to store data. Obviously, a machine that has 16 bits will store less information and cover less range than a machine that has 32 bits versus a machine that has 64 bits. That's what range is. Precision, again, can be related to the number of bits. If you think about floating point arithmetic, where we just showed you the mantissa and the significand, the more bits you have to represent the data, the more accurate it would be. So that's precision and accuracy. So just read through these chapters, and if you have any questions, please let me know. Accuracy refers to how closely a numeric representation approximates the true value. Precision of a number indicates how much information we have about that value. Okay. So read through this, and if you have any questions, please let me know. Character codes is an interesting concept. It's just how computers represent character codes, how we represent the languages, and most of the character codes that we learned in this class were based off the Latin language. The ASCII character code, for example, was based off Latin. I think you can read through that, and that's covered in one of the sections of the book, right? So until recently, ASCII was the dominant character code outside of the IBM mainframe. Okay, but I think today Unicode is the most popular one. Let me see here. So the Java programming language uses Unicode. Unicode code space is divided into 6 parts. That one you can learn in the textbook. Nothing for us to cover here, but again, most systems today embrace Unicode, which is a 16-bit system that can encode any character, every language in the world. So that's what's so cool about Unicode. So not ASCII. ASCII doesn't encode. ASCII cannot encode certain characters. Okay, Unicode is what a lot of computers use today to encode all the characters in all languages in the world. Error detection. So real quick, CRC is one of the most important error detection that I recommend you folks cyclic redundancy check, and it's really about some bits are appended at the end of the information that you want to send, and there's some binary division that is used by the computer to determine if the bits have been compromised. Okay, so there's some polynomial mathematics there that occurs. I don't expect you folks to really understand this fully, because in this course we're just doing a quick introduction of this, but the idea is that there's some bits that are added at the end of this information that you want to transfer. The number of bits is accepted or is negotiated both by the sender and the recipient. So let's take this example, for example. Let's take this one, for example. Let's say that the information that you wanted to send is represented as 111, this right here. And let's say that the divisor is this 1101. Let me just check to make sure that I'm talking about the right terminology here. Let's see here. Okay, so this is a divisor. A divisor, a number by which another number is to be divided. A number by which another number is to be divided. So this is divisor. Okay, so let's say you were sending 111101 through a computer. You, the sender, could negotiate with the recipient that there's going to be a CRC checksum of 1101. That checksum is appended to the end of the message. Now, if you go into your textbook, chapters 109 talks about this, okay? So the CRC, cyclic redundancy check, is appended to the end of the message. And the way it works to validate if the information is correct is that there's some kind of division that happens, like binary division. And you keep doing, you just try to, just really generally binary division. And you do the division until, like, that's what's happening here. You get to a certain point where you get a number, and that number becomes the CRC check. So let's see here. If no bits are lost or corrupted, dividing the received information string by the agreed upon pattern would give a remainder of 0, right? So for example, if this was the data that was transmitted, and if this bit pattern 1101 was the CRC data appended to the end of the message, the way the algorithm works is that you just start dividing the information bits by the CRC bits. You keep dividing until you get a 0 at the end. If you do not get a 0, then that means that the information has been compromised. If you get a 0, right? If you get a 0, it means that the information was not compromised. So it's an interesting algorithm. We may have a project for you guys to come up with some CRC algorithms to write some code on this if you folks have some programming language experiences. Otherwise, it could be an interesting project that we can do as an exercise in this course. Okay? So that's what the CRC, the cyclic redundancy check, is all about. Now, they say real applications use longer polynomials to cover larger information strings. You can imagine, you've probably seen CRC checks in a lot of things. Zip files, data that you download from the internet. Computers really use polynomials, long polynomials, to compute these CRC checks. Okay. So I think I have a video on this. I sure do. Yes, I sure do. So I will send this as part of the week 2 announcements. You folks can read through the CRC. And if you have any questions for clarifications, please let me know. There's some other interesting ones. Hamming codes and Reed Solomon are not as popular as CRC. You can read through those just for informational purposes only. But I think the one that you probably want to pay attention to is the CRC check. Okay, and then there's some formula here just to kind of formalize some of these things. But again, like I said, a lot of information out there that can help you all to kind of decipher and to fully understand the CRC check. So I did a lot of talking here. I hope this was helpful. A lot of stuff, again, this is going to be a lot of content, but I am providing you folks YouTube videos that can help you to understand some of these concepts. Your textbook is there. There's so much resources that can help. Again, I'm always available, emails. Send me an email if you need some clarification. I'll try again to respond within 24 hours, but I always try to respond at least 48 hours, but I'll do my best. If you need any clarification, let me know. If not, go to YouTube. Hopefully these videos help. And again, if you have any questions, please feel free to reach out to me. Okay? Thank you. Good luck. And I will see you folks in the next video. Thank you.